Hello. So this is the lecture number 2 for this series. So today we will be seeing about a RC circuit, first order RC circuit in series with a step source. Let the voltage prior to the like suppose let us incorporate a switch over here. This is the switch S, which is closed at t equal to time t equal to 0. And let us assume that the initial value of the capacitor voltage is V0. Okay, so now we need to find the response of this circuit. So what we will do is, for this circuit, by applying KVL, what we can see is, like if we consider a current I flowing in this circuit, so this current is nothing but V. Suppose by if we apply the KVL, what we get is V minus IR minus of V0 is equal to 0. So V minus V0 is equal to IR and I is equal to V minus V0 upon R. Okay, so this current is the same current that is flowing into the capacitor, and as we know that the current through a capacitor IC is given as C into dVc upon dt. Okay, so in that case we can write this current I as C into di by dt, sorry, C into dV by dt is equal to V minus V0 upon R. Okay, now we take the Laplace ट्रांसफॉर्म. ओके, तो हम लोग यहाँ पे लैप्लास ट्रांसफॉर्म लेते हैं. तो लाइक जस्ट टू रिकॉल मैं यहाँ पे फॉर्मूला लिख देता हूँ. जो डी एक्स बाय डी टी, इसका अगर लैप्लास होता है, लैप्लास ट्रांसफॉर्म, सो व्हाट वी गेट इज एस इंटू एक्स ऑफ एस minus of x at 0 minus. So this is the formula, so that we will be using here. Okay, and the second thing is, if we are having a step source like v of s v, so if we take the Laplace transform we get v of s upon s. Fine, so we will proceed in the similar manner. So from equation number 1, from 1, what we can write, we can write C into dV by dt. So we will like convert it into the Laplace domain, so it will become s into v of s minus v of 0 minus is equal to v of s minus v of s upon s into r minus v naught of s upon r. Fine. So one question that would be coming into the mind is, why didn't we consider v naught to be v naught upon s? तो ऐसा इसलिए है क्योंकि इट इज़ नॉट अ स्टेप सिग्नल, वो स्टेप नहीं है. सो दैट इज़ नॉट अ कांस्टेंट, दैट इज चेंजिंग विद द टाइम. सो दैट इज़ व्हाई we are not taking v naught upon s. So if we solve this, what we get is c into s v of s minus c into v of 0 minus is equal to v of s upon s into r minus v naught into s upon r. Right, so we will take the terms common. Okay, the terms that are common we will take, and now what we will be doing, is, yes, so we will take the term Vc of C into Vc. Okay, let us consider, the voltage through the across the capacitor to be Vc, suppose Vc of S. So like what we will obtain is, we will obtain, so we need to write here Vc at 0 minus. Okay, so now what we obtain is, we obtain mm, we obtain Vc of S. Let me write it from the beginning. 1 minute. Let me write it from the beginning. Some of the changes are required. So what we will do is, we are considering the voltage through the capacitor to be Vc. So we are writing Vc, and then we are writing V by R minus small Vc by R. Okay, so now अब क्या है कि हम लोग इसका लैपलास जब लेंगे तो वो होगा s इंटू वी सी ऑफ एस माइनस वी सी एट ज़ीरो माइनस is plus Vc of S upon R is equal to V of S upon Rs. Okay, उसके बाद C into S Vc of S minus C into Vc at 0 minus plus Vc of S upon R is equal to V of S upon Rs. अब इसको हम लोग अरेंज करेंगे. So we will take the term Vc of S common. We will get Cs plus 1 by R. Okay, और इधर आएगा V of S upon Rs plus C into Vc at 0 minus. Okay, so Vc of S is nothing but V of S by Rs into R upon 1 plus RCS. Okay, plus C into V at 0 minus into R upon 1 plus RCS. Okay, so if we take the terms RCS from the denominator as common, so so this R and this R will cancel out. So what we will get is, we will get V of S upon SRC S plus 1 by RC. We have taken the RC as common, so V at 0 minus upon S plus 1 by RC. This is what we will get, Vc of S. Okay, so thereafter now what we see, we can like we can this term can be like divided in by using, this term can be solved by using the partial fraction, and we will consider this whole term as a of S upon plus b of S plus 1 by RC. Let us consider, and this we will keep it like this. Okay, fine. Now we have to find a and b, the constant a and b. So how to find? A is equal to V of S upon RC S plus 1 by RC at S is equal to 0. So when we will put, we will get A equal to V of S. Okay, then similarly we will find B, and B is nothing but V of S upon RCS at S is equal to minus of R by minus of 1 by RC. So it is nothing but minus of V of S. So we will put this value of A and B in the above equation. So what we get? We get Vc of S is equal to V of S upon S minus of V of S upon S plus 1 by RC, and plus V 0 minus v0 minus uh, upon s plus 1 by rc. Okay, so now the final step is taking inverse Laplace transform. Now we will take the inverse Laplace transform. So the formulas that will be used here, just to remind, I will write it down. The first one is, if we have v of s upon s, so if we take the inverse Laplace transform, we will get v, okay, v. And the second thing is, if we take the Laplace transform of 1 by s plus a, we will get e to the power minus of at. And these are the two formulas that we will be using right now to take the inverse of this Laplace transform. Please note it down, it will help. So now going back to the time domain, we will see that it will become Vc of t is equal to v minus, it will become v e to the power minus of 1 by rc into t, and plus v at 0 minus e to the power minus of 1 by rc into t. So we can take these terms as common. Okay, so we can take these terms as common. We will write v minus v plus v at 0 minus minus of v e to the power minus of 1 by rc into t. So this is nothing but vc of t. So if we like see the circuit, so we had a r, we had a c, and there was a source v. This capacitor will store the energy as soon as the switch S is closed. Suppose we take a switch S. As soon as the switch S is closed at t equal to 0, the capacitor C will start storing the energy, and soon its voltage will start rising. And at a time, certain amount of time, the capacitor's voltage will rise and it will reach the level of the input voltage source V. So therefore the current through the circuit will become 0. So this is indicated by the circuit. So we can conclude from this whole thing that a capacitor, point number 1, capacitor behaves as an open circuit at steady state, and capacitor behaves as a short circuit at the switching, that the initial state. It means whenever there is a sudden change in the position of the switch, so in the initial the capacitor will behave as a open, there's a short circuit. So like it will not offer any resistance to the current. So this is the important formula that we got. So we can generalize it in this form. We can write it as Vc of t is equal to, so v this v is nothing but the final value attained. We can write it v at infinity plus v at 0 minus of v of infinity e to the power of minus of 1 by rc into t. Fine. So this is the final form that we get. We will see the plot for this. If we see the voltage Vc of t as with the time axis, we will find that at t equal to 0, comma Vc of t, if we put t equal to 0, what we will get at t equal to 0, from this equation, from equation number 2, we will get Vc of t equal to V. Okay, you can calculate it by putting t equal to 0. You will get Vc of t equal to V. And similarly, at t equal to infinite, we will get Vc of t is equal to 0. Okay, so if we plot the voltage of the capacitor with respect to the time, we will get the curve somewhat like this. Okay, and like there will be a time when the capacitor's voltage will degrade to 36.8% of its final value, and that the time taken by the circuit to reach 36.8% of its from this final value will be known as the time constant tau. And this tau time constant is nothing but 1. This is nothing but RC. This is an important point to note down. So in RC circuit, the time constant tau is nothing but the time taken by the voltage of the capacitor to degrade to it 36 point to 67%, like the to degrade to 36.8% of its final value. Okay, so this is the current, this is the voltage plot of the capacitor. So it was an important discussion. So please take a note of all this and try to solve it once by yourself. You will get a clear concept of it. Thank you.